And the probability of bit error is about 9f squared to leading order. Okay, so Shannon asked the question, if we make encoders and decoders, where can we get to on this diagram? We've had a few ideas, repetition codes, and I've shown you one code using parities. The question is, what's the boundary between achievable and unachievable points on this diagram? And before Shannon conceived of asking that question, I think conventional wisdom was that the boundary between achievable and non-achievable points just had to be some sort of line going through the origin. Because Sod's law says if you want a really small error probability, then surely you're going to have a really small rate, just like our enormous stack of disk drives that we're imagining. So conventional wisdom knew that points over here were achievable, but conventional wisdom probably was assuming that the boundary went somewhere here. And Shannon proved an absolutely remarkable result. And this is going to be the heart of this sequence of lectures to prove this result. Shannon proved that you can get the error probability arbitrarily small without the rate having to go to 0. So Shannon proved that the boundary between achievable and non-achievable points is a line that looks like this. Everywhere here is achievable, and excitingly, this line meets the rate axis at a non-zero rate. And because that's an exciting place to talk about, we give it a name, and we'll call it C, the capacity of the channel that we're discussing.